Hello, hear me in the back? Yes, good, all right. Welcome to Data 8, Lecture 30. Today we're going to be talking about correlation. I think my only announcement for today is that homework 6 is available. So it was released yesterday afternoon, and it is due Friday at midnight. Oh, and my other announcement is congratulations on finishing project 2. Woohoo, good job. You guys don't seem very happy about finishing project 2. All right, let's try it again. Congratulations, you guys worked hard on the project. Good job, everyone. Cool. Do we have tutoring spots available, Emma? Oh, yes, so there is tutoring spots available, I believe, on Thursday. So if you wanted tutoring, please sign up for tutoring on Thursday. All right, let me do a quick recap of what we did yesterday. So yesterday we asked a question. OK, so we see that our confidence intervals get smaller as we increase our sample size. Is there a way to actually tell for certain what sample size I need in order to get a confidence interval that's this amount of wide? OK, that's this wide. So we know that the central limit theorem says that the distribution of a sample mean or a sample proportion, because those two, remember, are really the same thing. The sample mean sample proportion is roughly normal, and it's going to be centered at the population value. So either the population mean, if you're looking at means, or the population proportion, if you're looking at population proportions. OK? It turns out that the confidence interval uses this very same distribution. So this distribution right here, the confidence interval uses the same distribution to make a confidence interval. So the central limit theorem says, when I make a confidence interval, that distribution of values I'm taking the middle 95% of, that distribution will be roughly normal. Because it's normal, that 95% confidence interval will be, the middle 95% will be the middle plus minus 2 standard deviations. Okay? I can say that because I know that that distribution of values is going to be roughly normal. So that means that my confidence interval will be the center of my distribution plus minus 2 standard deviations. That will give me about 95% of the area there. Okay? So because we're taking the center plus minus 2 standard deviations, the total width of that confidence interval will be 4 standard deviations. Right? So 2 on the left side, 2 on the right side, total of 4. Right? So if we want the total width of the confidence interval to be small, or smaller than some number per se, we want to say, OK, make 4 times the standard deviation small, because that's the width of my interval. If I can make this small right here, I can make my interval small as well. Right? So the way we do that is we note that this standard deviation here of the sample proportion happens to be the population standard deviation divided by the square root of my sample size. So we had this formula here, which is basically just taking this and plugging in the standard deviation based on the population, which we saw a couple days ago. Right? So we have the width of my confidence interval is 4 times the standard deviation of my population divided by a square root of my sample size. This says, for instance, that if I quadruple my sample size, my total width will go down by 2, by a factor of 2. Okay? So if I quadruple my sample size, square root of 4 will become 2, and the total width will be divided by 2. Okay? Now, we asked a question yesterday. Suppose I want my width of this interval to be less than or equal to 3%. We're looking at proportions. I want the width of the interval to be less than or equal to 3%. Okay? So what I'm doing now is, OK, this slide kind of has a lot going on. So I'm taking this right here, which is the width of my interval, and I'm saying I want my width to be less than or equal to 0.03. Okay, so I'm just taking this right here, putting it right here, and making it less than or equal to 0.03. So the idea here is if I can solve for my sample size, I can get a sample size that I need to take in order to get my interval small. So I want to ask this question before I go out and take my samples, so I can make sure that my confidence interval is as small as I want it to be. So this equation right here relates my sample size with everything else. So if I solve for a sample size, so this line right here is just rearranging the terms, so I get the sample size on one side. You can do that yourself with some algebra. And what I get is the square root of my sample size should be greater than 4 times the standard deviation divided by 0.03, with just some terms rearranging here. All right? So the idea here is, OK, if I can just solve for the sample size, I can get the sample size that I need to make my confidence interval smaller than 0.03. So then we had the question. I was supposed to show up one at a time. Then we had the question. OK, so let's go through this line by line. The question, OK, we have this equation here. We want to compute the right side and then square the whole thing so we can get the sample size. But we don't know the standard deviation. right? We don't notice standard deviation with population because we can't look at the population. But we happen to know, we saw yesterday, that if my population is zeros and ones, so for example, the amount of people that vote for candidate A is a 1, and if you didn't vote for candidate A, you're a 0 in my population. If that population is zeros and ones, then we know that the standard deviation of the population will never be bigger than 0.5. And that is a very key fact because it allows us to plug in 0.5 into the standard deviation of my population. So I plug in 0.5 into the standard deviation here, plug and chug, compute, square the whole thing, and we get the sample size is greater than or equal to 4,444, which is, we round up because we want like the next biggest number, so we get 4,445. So that's the whole process of choosing a sample size to make sure that the confidence interval is sum width. Any questions about that? Yes?
Would the standard deviation of any population that just has like two choices be less than 0.5?
Yeah, it's a good question. So Saeed is asking, will the standard deviation of any population that only has two choices be less than or equal to 0.5? That is actually true. If you take those two choices and mark one set of them with ones and mark the other set with zeros, if you take like A's and B's and change them to ones and zeros and take the standard deviation of the ones and zeros, it will never be bigger than 0.5, which is highly convenient for purposes like this. Yeah?
Is there a way to do it if we have a different type of population that's not just zeros and ones?
Yeah, so is there a way to do this without, if we don't know the population of zeros and ones? Unfortunately not. Unfortunately not. So we don't know because if the population can be any number, the standard deviation can also be any number. If we don't restrict the population, the standard deviation can be as big as we want it to be. Okay. Any other questions? All right, so I want you to try out this discussion question, which should look pretty familiar to you because we just did it. Okay, so try this out with your partner. I want you to, so the question is, I want to estimate what percent of voters will vote for candidate 3. So I want my confidence interval to have a width of 3% or less. We know the answer, but I want you to just work it out with your partner. Just start with the equation and work out the algebra so you get a sense of how it works. You know the answer, but try it out. Go ahead. So I actually want you to try it out. So take the equation, take out your computer or calculator if you want to. Make sure you can get back the 4,000 number because I'll need you to do that in the future. Okay, so make sure you can get back that 4,000 number.
Do we multiply like the original standard deviation by 4 because that allows you to encompass like 95% of the responses? Or?
That's right. Mm-hmm.
Deviation of zero population is 0.5. Which is 4 times those 2.
Okay, how many of you guys are able to get back 4,445? Concerningly few of you. How many of you guys were able to get back 4,400? Raise your hands again. So you did this problem and you got back the number. Question mark? Yes, yay, nay. All right, well, whether or not you were able to do it now, you should be able to go back and do it. Okay, so you can try tweaking these numbers to get different problems. So what about a width of 5%? What about a width of 10%? What about a 99% confidence interval? What about a 90% confidence interval? You should know how to like tweak those parameters and still get the sample size that you need to get in order to make that confidence interval the size that you want it to be. Okay, so it's okay if you can't do this. It's okay if this confuses you and you can't do it right now, but you will have to do it eventually. So make sure you know how to do it at some point. All right. So we're going to move on to topic for today, and we're going to talk about prediction. Okay, so we wrapped up our stuff about inference. We now have some of the building blocks we need to talk about prediction, and so I want to introduce the topic to you today. The basic idea of prediction is, if I know one characteristic, I want to predict another characteristic. So for example, given my height, how tall will I be next year? Probably the same height, since I think I stopped growing. Okay, so what about given my height, how tall my kid be as an adult? So that I don't know, but I can predict. I can also predict seemingly unrelated things, such as given my height, how much will I spend on a boat? I've always wanted to go sailing. Who knows how much I'll spend? Okay. So the basic idea here is every question in this case has two characteristics. I know something, I don't know something, and I'm trying to use what I know to predict what I don't know. Another key basic assumption of prediction is that for some sample, we know all the characteristics. So for example, I have some prior data that has parents' heights and kids' heights. So I can say, OK, based on the trends that I've observed before, let me try to predict the future. So without prior knowledge or without like the prior data that you have, you won't be able to do much about the future because you have no idea. Okay, so that's kind of the basic idea of prediction. So the only way we can predict, only way we can make good predictions is if our two characteristics are correlated. So correlation in this case, what I'm referring to is an association. So if there's no relationship between my current height and how tall I'll be next year, I will never be able to predict how tall I'll be next year given my current height. Right? If there's no relationship between my height and how tall my kid will be as an adult, there's no way for me to predict how tall my kid will be given my height because there's no relationship at all. Right? So prediction makes this basic assumption that I need my two variables to be correlated or associated with each other. And because of that, I can make predictions. Okay? So correlation. There are some terms here that I want to clarify first of all. So some vocab terms for you. We looked at one of these terms as what we call association between two variables. Association basically means if I change one variable, does the other variable change as well? Okay, so if I change my height, will I tend to have taller kids? Right? So we've seen that term before when we talked about hypothesis testing. Right? We use hypothesis testing to establish an association, although we don't know much else about the association with just a hypothesis test. In particular, sometimes we want to know the trend. So whether or not the association is positive, so if I increase the height of my kids will go up, or negative, if I smoke, the weight of my babies will go down. Right? So two different directions of association here. That's what we call a trend. And we also want to know the shape or the pattern of my relationship. Okay? Pattern in this case is kind of a subjective term. It really just means, for our purposes, any discernible shape. So typically the way that we'll look for a pattern is, especially in the case where we have two sets of numerical data, so for example, parents' heights and kids' heights, we use a scatter plot to look at the pattern of the data. Patterns that we'll look for in this class are linear patterns. So when the data on a scatter plot look like a line, or nonlinear patterns where there can be any other shape. In general, what you want to do when we're doing prediction is you always want to visualize first and then quantify whatever it is you want to do. So we're going to be learning about some different statistics in the upcoming few days. But basically, the rule of thumb is before you compute any of these numbers, you always want to visualize your data first, because that can give you some hints about what to do. All right, so let me show you some data. And OK, here we go. Make that bigger. All right, so here I have some data on car sales, in particular hybrid car sales. So I have here, for example, the Prius was released in 1997. The MSRP is the manufacturer's set price. So the manufacturer set the price of this retail price to be $24,000. It has this acceleration, so like miles per second, I think. And here I have the MPG. Here's a class. Okay, so I have a bunch of cars here, how much they cost, acceleration, miles per gallon. Let's take a look at whether there's a relationship between acceleration and how much you pay for it. Okay, so think in your head, what do I think cars will cost as the acceleration goes up? Let's take a look. Hybrid.scatter, and that's not too bad. Acceleration. Okay. MSRP. Let's take a look, and let's see what we have here. We see here acceleration on the x-axis, MSRP on the y-axis. We see here a positive trend, right? As my acceleration goes up, so these cars accelerate really fast, but they also tend to cost a lot. These cars don't accelerate a lot, or these cars accelerate kind of slowly, and they cost little. All right, so that's kind of an association there. Is this linear? It's a little hard to tell, because like this section right here looks like most of the cars are down here, and this section up here is kind of spread out and scattered. Hard to really tell whether that's linear or not. Let's take a look at another case. So let's ask the question, all right, how much does miles per gallon relate with MSRP? All right. So I have this. Let's plot miles per gallon and MSRP. How many of you guys think that there'll be a positive relationship here? So the more miles per gallon, the more you pay. How many think there's a negative relationship there? More miles per gallon, the less you pay. No one believes that. All right, well, let's find out. And lo and behold, what kind of society do we live in where you pay more for cars that are less fuel efficient? Well, if you look at what's happening here, we see a negative association, right? So here we have some cars that are really, really fuel efficient, and you paid not that much for them. Here, all these are cars around 20 miles per gallon, you pay a ton. Let's take a look. So this data here also does not really look linear. Not so sharply sloping downward part here. So it looks kind of like an L shape. Yeah, Kevin?
So could you describe that pattern as like y equals to 1 over x or a harmonic series?
It's hard to say. Hard to say. Because there's lots of different relationships that have a downward curving thing like that. It's really hard to say based on just looking at this what kind of relationship it is. Usually though, if the relationship is linear, it'll be not super hard to tell. Okay. But when it comes to curves, we're kind of bad at looking at curves and trying to figure out the relationship there. Let's just stick to linear for now. Okay, that's a good question. So I noticed here there's kind of like one chunk here with a bunch of cars that are really not that efficient but cost the most, and some here that are really efficient but cost the least. I wonder why that could be. Cost a lot also tend to be SUVs. Okay, so we have here. So you see in this table, we have some small cars and some big cars. It turns out that in this case, these are all hybrid cars, right? These are all hybrid cars. And it turns out in this case that the cars down here are all smaller cars, so they have higher miles per gallon and also tend to cost less. The cars over here are bigger cars, and they have less miles per gallon. So let's take a look at just the SUVs. So I want to take from this table hybrid dot where the class of car is an SUV. So we have here just the SUVs. Let's save those. And how much they cost. All right, so here we go. So what do we see here? We see here that all the SUVs fall into like the 20 to 30 range, whereas before they go from like 20 to 70. Right? So all the SUVs are not super fuel efficient. And the prices of the SUVs are pretty high. So here we have 100,000, here's like 60,000, here's like 40,000, which corresponds to like 60,000 here, 40,000 here. Right? So SUVs, not super fuel efficient and also cost more because they're bigger. But we can see here that this looks kind of linear, right? So the data here have about the same amount of like variation around what we can imagine a line would go right here. This data looks pretty linear. And let's see if we can describe it some more. So we can also take the SUVs and look at the acceleration, see if that's linear as well. So let's take this, look at the acceleration compared to how much it costs. So here's just that. So we can see here that the acceleration, the relationship between cost and acceleration is also kind of linear with some random points out here. I would say minus those points, it looks pretty linear, although it's kind of hard to say without some more numerical quantities. Okay, so what I want to do now is compare MSRP with MPG. All right, and it's kind of hard to do so. So it's kind of hard to do so because these are different units, right? This is dollars, these are miles per gallon. This is like 70,000 here. This is like 28 miles per gallon here. So it's kind of hard to directly compare those two. What I can do to get a better comparison is to convert them to standard units. So if you remember, the way to convert things to standard units is, so I have here some numbers. Let's take out the acceleration. Let's say, or let's take out the cost. Okay, so column MSRP. Darn. Do that. Have here some numbers. The way to convert to standard units is take the mean, subtract out each number from the mean, divide all of those differences by a standard deviation. Okay, so I have here the mean. I have here the standard deviation. Let's see if this will work. Oop. Darn. Okay, SD. There we go. And here's the mean, and here's the standard deviation of the cost column. So let's convert those to standard units. And this minus the mean divided by SD, and now they're in standard units. So what does this mean? That means that, let's take a look at this number right here. That means that this original price was about 1 standard deviation below the average cost. Whereas this one right here was about 1.1 standard deviations above the average cost. Okay? So converting to standard units there. I want to do this a bunch of times today, so I'm going to write a function to do that for me. Oops. Let's write the function. So let's call this function standard units. We can convert any set of numbers to standard units, so I'm going to do that. So if I pass in any set of numbers, I want this to go here. So here's nums, and I want to return nums minus mean divided by the SD, just like that. Okay. Now I can convert MSRP to standard units just as we've done just now. And bam. Same set of numbers. Here's -1. Here's like 1.12. Right? Cool. Any questions about that? Excellent. OK, so now let me just do a quick attention check. So if I make this table, let's have 2 columns, MSRP. Let's put the original MSRP here. So here's SUVs. Here is a column. Let's also put the MSRPs in standard units. OK, so I'm going to do that. Put that in there. Bam. What if I scatter plot these two? I'm going to scatter plot the MSRPs with the MSRPs in standard units. What do I get back? Talk it over with your neighbor. What should I notice?
It's a standard formula as well.
All right. So let's see what happens. Run that, and bam. We see that it's linear. Why is it linear? It's linear because it's normal. Why do you say that? Yeah, I kind of see what you're saying. So you're saying, OK, every number here has like a corresponding number in standard units, right? So I think the term normal there you should be a little careful of, because we don't know whether our data are normal or not. The cost might not be normal for cars, but when we convert to standard units, the key thing to notice is that if I go up in cost by another $10,000, so I go from $60,000 to $70,000, that's like an increase of about, looks like here, maybe like 0.5 on the y-axis. If I go another $10,000, that's another increase of about, let's say, like 0.5 on the y-axis, right? So I can see that for every increase of x, there's the same increase of y, and that's a linear relationship. So that means that every point here, stays on this perfect line that goes up like this. Okay, so that's not super important. I just wanted to kind of get you thinking about standard units and how those relate back to original units. So when I take original units and convert them to standard units, I'm not doing a whole lot with the data. All I'm doing is, you notice here that most of the points are around 0. I'm taking my data, moving it so that the center of the data is at 0, and then either shrinking it or stretching it so the standard deviation is 1. That's the key idea here. So I'm just moving my data and shrinking it or stretching it so the standard deviation is 1. That's the key idea behind using standard units. And if I do that for both MSRP and miles per gallon, both sets of data are at 0, standard deviation of 1. That lets me compare them more easily. OK, so let me ask you another question. All right, so here's a line 0. I notice that most of my points are around 0. Right? Are half my points above 0 and half my points below 0, or what else is going on? Talk it over with your neighbor. Do you think half the points is? Do you think it's half and half, or do you think it's something else? Go ahead. All right, so how many guys think half the data are below, half the data are above? How many guys think it's not exactly half? Not exactly half. Nice thinking. So it turns out that if I want the number where half the data are above and half are below, I'm looking for the median. Looking for the median of my data, right? But it turns out that 0 here is the mean of my data. And it looks like here, because I have some points that are way out here, so here are some points here, it looks like the mean is going to be higher or lower than the median. It looks like in this case these numbers are high, so my mean will be higher than the median, right? That means that my median is probably somewhere in here. So half the points are here, half the points are here. The median is probably somewhere here, below 0, and the mean is going to be 0 because I convert to standard units. Okay, so another question about means and medians, I can find out by taking this. How many of those are above 0? And figuring out the proportion of those. So here is np.count non-0. Take that, divided by the length of this. This is getting kind of long, but let's see if we can do this. Length of that column. It looks like, indeed, only about 46% of my points are above 0. More of them are below 0. OK, so that's standard units. I have here a function that you can look over in your own time. You should be able to write this yourself. But what I'm doing here is I'm just writing a function that if I pass in a table, it will convert all the columns to standard units. Okay, so what I have here is if I have my SUV table, I want to convert both miles per gallon and MSRP to standard units. So what I'm going to do is select them out, pass them into my function, and now I have both miles per gallon and MSRP in standard units. So here they are in standard units. Let me make that a little smaller. OK, so there it is. And now I can plot them on a scatter plot, as I did before. OK, so let me take that. Take that table, the scatter plot, MPG on the x-axis, MSRP on the y-axis. And what do we get? We get this. I'm going to fix the limits. We know that because of Chebyshev's inequality, that a lot of my points will be within like 5 standard deviations of 0 because these are in standard deviations. So I can set my limits to between -5 and 5. It turns out that in our case, all of my points are between -3 and 3. So I'm just going to do that. So plt.xlim, -3 and 3. Same with the y-axis. And here I just have, so what I'm doing is I'm just making the 0, 0 in the middle of my scatter plot here. So run that. So here is 0, 0. Here are all my points. We see this. Let's compare it to what we had before. Right? So before we had SUV. Okay, I'm going to scroll up. SUV.scatter, MPG, and MSRP. Compare these two. And there we go. Okay, so before, after, before, after. You'll notice, so let's suppose I don't change the limits here. Okay, what do you notice? It looks almost the same. In fact, it is basically the same. Right? So again, the reason why it looks the same is because when I convert to standard units, I'm not like moving points away from each other. I'm just taking all my points, moving them all down to center at 0, and then squeezing them and stretching them. Right? So depending on how, so basically what I'm doing is moving all these points to be centered at 0, 0, and then changing like the way the points are spread out so that it looks like most of them fall between -3 and 3 on both axes. Right? So here we go. Standard units. OK. I can do the same thing with my acceleration and the cost. OK, so here, let's put, oops, keep that there. Keep that there. Acceleration. Take a look at what that looks like. So again, if you were to compare the two plots of acceleration versus cost before and after standard units, you will see the relationship to be looking pretty much the same. Pretty much the same. Okay. But you notice here that it's centered at 0, 0. That'll become important in a second. But just know that the basic idea behind why I'm doing this is because my two axes used to be in different units. Right? This used to be dollars. This used to be like miles per second or something. And what I'm doing here is when they're both in standard units, this point right here, so this point right here, this point that's close to like 1, 1, 1, 1, this point is both 1 standard deviation away from the average acceleration and 1 standard deviation away from the average cost. Okay, so that lets me compare both axes. All right, so and click that. Click that. All right, here we go. All right. So we saw that we have some scatter plots. We looked at the relationships between different variables. Sometimes we get a positive sloping relationship. Sometimes we get a negative sloping relationship. It turns out that there is a number, a statistic that we use to describe linear relationships, and that's called the correlation coefficient, okay? Otherwise known as R. You'll see that quite a lot. The basic idea behind this number, so it's a number, and it measures linear association. Okay? So it doesn't measure whether the data are like a perfect curve or a perfect like parabola or whatever else you have. It only measures how well they fit onto a line, so only linear relationships. It's based on standard units, so we'll see how to calculate R based on standard units in a second. But the basic idea is this number can go between -1 to 1. It will never go beyond those numbers. And if R is 1, then what we have is a scatter plot is a perfectly straight line sloping upward with some slope. Okay, so it could be sloping upward like this. It could be sloping upward like that. Or I guess for you guys, okay, so sloping upward like this or sloping upward like that. Right? But as long as the data fall on a perfectly straight line and don't deviate from that line, R will be 1. R -1 would be a perfectly straight line sloping down. So let me think. For you guys, it'll be like this, right? It could be like this. It could be like this. But as long as they're sloping down and all the points are all in that straight line, it'll be -1. If R is somewhere in between, then so depending on what R is, there is a linear relationship or a weak linear relationship or no linear relationship, but the points will not be on that perfect line. So we could have a point off the line, a couple points off the line, or a bunch of points not really on the line, but kind of in the same linear relationship. That will change my value of R to be something besides -1 and 1. In particular, if r is 0, then there's no association, which means that my points are uncorrelated with each other. Knowing one variable does not help me figure out the other variable. So let's take a look. I have here a little demo that I want to use to illustrate the idea of r. Okay, so this function right here, which you don't know how to write, I'm just going to use it as a demonstration. So here, I'm showing you a plot of points that have a correlation of 0. Okay, so when r equals 0, my points are just a cloud. What does this mean? It means that even if I go from 0 to 2 or 0 to -2, it doesn't give me any sense of what y could be. If I know x, I can't figure out y. These points are uncorrelated. That's an r of 0. On the other hand, if I change r to 1, let's try that. Let's see. Try that. There we go. All my points fall on a perfectly straight line. Same deal here with -1. Okay. If I go in between, so now let me take this slider and go in between -1 and 1. If I go up a little bit, still downward sloping, but the points are in a cloud, right? Not perfectly on that line. As I get closer and closer to 0, you'll notice that the points look more and more cloudy, and then now I just have a blob. This is a shapeless blob, no correlation. If I keep increasing r, then my points will become more and more like a line, positively sloping, and finally, when they reach 1, a perfect line. Okay, so different values of r result in, or different values of r describe different types of plots. Okay, so the way to compute r is actually not too hard based on what we have here. So if I have this table with x's and y's, these are just some made-up numbers I'm using to demonstrate the calculation of r. So I have this table here. The way to calculate r, let's scatter plot this. Visualize first. Okay, so scatter plot, 0, 1. So it looks like here we have kind of a positive relationship. Knowing the value of r will let me determine how strong that relationship is, right? So if all the points are perfectly on a straight line, then r will be 1. And that'll let me quantify how good of a linear relationship that is. On the other hand, it looks like not all the points here are on a straight line, but they look kind of close. The axes here are like really zoomed in, so the points are kind of close to each other. We can use r to quantify exactly how strong that linear relationship is. Let's take a look. The way we calculate r is take my table and convert it to standard units. And it didn't work. But let me see, standardize, I believe. Standardize. Here we go. Standardize. Okay, so convert them both to standard units. Let me call that t standard. Okay, so there it is. I'm going to multiply all my x's and y's together. So I'm going to take my t standard, take that first column, multiply it by the second. That. There we go. Multiply them all together. These are my products of my x and y in standard units. So let me add that to my table so we can take a look at what those numbers are. So take that width column. Let's call it products. Put this guy there. Yeah. So we have here x in standard units, y in standard units. We multiplied each x with its y value. Here are the products. And the correlation coefficient r is just the average of these products. Let's figure out what it is. So take this, and I'm going to call this, let's say, I can just take these numbers. So here are my numbers, my products, np.mean. And there we go. We see that my correlation coefficient is 0.6. Okay. So not 1, because not all my points fall in a straight line, but not 0, because my points are not in just a random cloud. It looks like there is some positive trend, right? A positive trend, and we see that because my r value is between 0 and 1. Any questions about that? OK, so what I'm showing you now is just a definition of r. Okay, so the definition of r, the way to calculate it is, I think I have a slide here. Let's do that. Excellent. All right. The definition of r is y in standard units, x in standard units, multiply them together, take the average. That's r. Okay. So let me, oh, one more thing. And R measures how clustered a scatter plot is on a straight line. We've seen that a couple of times already. So let me close attendance. Any objections? OK. So we have here a way of calculating R. I want to calculate R for a bunch of different things. So let's define a function called correlation. And let's say give it a table, give it an X column, give it a Y column. And I'm just going to take this, turn. I'm going to call this T standard equals standardized T. Put that there. I can just replace this with X, this with Y. And now I should be able to calculate the correlation of my T with column X and column Y. So this is just the same thing. Oops, what happened here? T is not in the table. OK, let's see. Try that again. Nope. T is that. Standardized T. Oh, I see. So I'm going to need to do standardize. OK. I want to just do this. So take my T table, take my column X, and standardize this. Standardize that. Make mistakes too. All right. Then multiply them together with this column in standard units. All right, let's try this and cross our fingers. And T. And it's concerning. Let's take a look. NP.mean. T.column X, question mark. Standard units. Darn it. I have all these standard functions that are confusing me. All right, that took a while. Here we go. So same thing. I have a function here. Computes my correlation. All right, so let's take a look at some of my other relationships. So here I have SUV.scatter. Let's compare the acceleration with the price. Same scatter plot. Now since I have a function called correlation, I can just do this all in one go without having to do like the whole mean, standard units, multiply thing myself. I can just call this function over and over again. So let's do that. And just replace this with correlation. And I see here that I have a correlation of about 0.5 between price and for the MPG. So here I have miles per gallon. Okay. A downward sloping trend, so we should see a negative correlation. It's not perfectly on a straight line, so the correlation should be between 0 and -1. Okay, so let's confirm that. Put that there, copy that. MPG. Indeed, it is negative 0.67-ish. Okay. So just to recap, we see here that we need to figure out, before we can do any prediction, we need to figure out whether there's a relationship between two variables. Okay. We have some ways of describing that relationship, and a correlation coefficient is one way we can describe the relationship between two numerical variables. They need to be numerical. Okay. You can't use this for categorical data because you can't find the standard units of like small, medium, and large. Okay. It doesn't work out. You need two sets of numerical data. That lets you calculate the correlation coefficient R. That gives you a measure of how correlated two variables are. Okay. The more correlated two variables are, the easier it will be to predict, right? So you saw in this case, let me scroll back up. Let's suppose I'm trying to figure out, okay, given some value of x, what my value of y is. If my two variables are perfectly correlated, I know for certain what value of y is given a value of x. On the other hand, if they're not as perfectly on the straight line there, given 1 on the x-axis, I can say, OK, it looks like here y could be maybe 1, maybe is 1.5, right? I have less certainty there. So the more correlation, the better. And now we have a numerical measure of correlation, R. We can use R to describe different data sets. And in general, we want R to be closer to 1 or closer to -1 when we're trying to do prediction. Cool. That's all I got. I'll see you tomorrow.